A very warm welcome to all our viewers. You are tuned into AI WorkOne, your definitive daily analysis covering the cutting edge of artificial intelligence, deep learning architectures, and high-performance computing infrastructure. Today is Tuesday, June 23rd, 2026, and we have an exceptional lineup of industry developments and technical analyses to dissect. In today's briefing, we will analyze the latest fluctuations in the cloud compute marketplace, focusing on H100 and A100 spot pricing and the stabilization of GPU rental structures. We will also dive into the architectural updates surrounding next-generation silicon platforms, the emerging consensus on scaling law limitations, benchmarks of the latest open weights frontier models, and the rise of unified execution environments for multi-agent workflows. Furthermore, we will explore the practical economics of local model inference, the scaling constraints of data center power co-location, prompt validation security guardrails, and compliance regulations governing algorithmic safety. As always, before we dive into today's analytics, we state our standard institutional disclaimer. The contents of this video are intended solely for educational, informational, and research purposes. This analysis does not constitute financial, investment, or professional engineering consultation. The hardware, software, and capital markets surrounding artificial intelligence are highly volatile and carry substantial operational risks. Please perform your own comprehensive due diligence, validate your system designs in isolated environments, and manage your compute budgets and data storage with appropriate caution. With those guidelines established, let us transition directly to the market dashboards, hardware metrics, and today's core analytical themes. We begin today's briefing with a detailed look at the current state of high-performance compute leasing and spot pricing. Enterprise rental rates for NVIDIA H100 PCIe instances on secondary cloud networks have stabilized at approximately $2.45 per hour, showing minor fluctuations but maintaining a consistent baseline. Meanwhile, legacy A180 GB instances continue to find steady demand at $1.20 per hour, and Google Cloud's TPU v5e remains highly competitive, holding its position at $1.35 per TPU hour. This price stability is closely coupled with a significant normalization of supply chain timelines. Lead times for high-density GPU cluster delivery from major manufacturers have decreased to 12 to 14 weeks, a dramatic shift from the long queues experienced over the past 2 years. This supply relief has reduced speculative booking, allowing tech teams to make calculated, infrastructure-led decisions rather than rushed, panic-based cloud commitments. For infrastructure architects and financial directors, this stable pricing window represents a valuable opportunity to evaluate hosting layouts. With the immediate scarcity threat receding, teams should transition from short-term, high-cost spot rentals to structured multi-year reservations or custom hybrid configurations. The goal is to optimize long-term operational costs by factoring in high-throughput network connectivity, physical co-location fees, and specialized engineering maintenance. Next, we turn to the fundamental limits of model scaling and the structural shifts occurring in foundational research. For several years, the primary path to building superior language models has been the brute force scaling of parameters, dataset tokens, and training compute. However, leading research institutes are now observing clear logarithmic plateaus, where scaling parameters by an order of magnitude yields only minor increments in general intelligence benchmarks. This scaling ceiling is primarily driven by the exhaustion of high-quality, human-generated training datasets. As a result, developers are shifting their strategies toward synthetic data generation pipelines, utilizing frontier models to generate, filter, and structure educational datasets. While synthetic data enables targeted reinforcement learning on complex reasoning tasks, it also demands rigorous sanity checks to avoid model drift and cognitive alignment issues. In response to these scaling boundaries, the research community is pivoting from training time scale to inference time compute. This shift emphasizes wrapping models in reasoning loops that perform multi-step search, tree-of-thought exploration, and verification checks before delivering an output. By shifting compute budgets from pre-training to runtime reasoning, developers are achieving major capability boosts without expanding raw parameter sizes. Our third block evaluates the latest benchmarks and the rapid advancement of the open weights ecosystem. The current generation of open weights models is demonstrating capabilities that rival closed proprietary models across standard reasoning, mathematics, and programming tests. This closing capability gap is fundamentally changing how enterprises plan their software product roadmaps. On standard programming benchmarks like human eval, medium-sized open weights models are regularly scoring above 86%. This high baseline capability is paired with expanded context windows, which now frequently exceed 1 million tokens, allowing developers to load massive logs, code repositories, and documentation sets directly into local memory. These features enable high-fidelity context processing without relying on closed cloud endpoints. This open weights acceleration presents a strategic choice for modern technology operations. While proprietary APIs provide low initial integration friction, open weights configurations offer absolute data privacy, zero API dependency, and the freedom to customize weights for specific domains. As toolchains for model optimization and execution mature, self-hosting is increasingly becoming the preferred architecture for security-sensitive industries. We now examine the paradigm shift from single-turn chat interfaces to autonomous, multi-agent execution frameworks. Rather than relying on humans to manually prompt models through complex workflows, modern system designs construct networks of specialized agents that collaborate, delegate, and iterate to complete complex business objectives. These agentic systems leverage advanced design patterns, including systematic self-reflection, strategic planning, and automated tool utilization. An agent in this architecture does not merely generate text. It writes executable code, runs it in sandboxed containers, analyzes execution errors, refactors its code, and queries external APIs or documentation to resolve gaps. This looping behavior allows agents to solve multi-step problems autonomously. For enterprises deploying these frameworks, the primary benefit is the rapid automation of complex software engineering, data cleaning, and customer support pipelines. However, running autonomous agents at scale introduces challenges in state management, infinite loops, and API usage costs. Modern engineering teams are focusing less on writing static prompts and more on building secure execution runtimes, structured tool access, and robust logging. In our fifth block, we focus on the practical benefits of local developer inference. The convergence of unified memory architectures on personal computers and specialized hardware accelerators has made running advanced local models on workstation laptops a standard, daily practice for software engineers. Using open runtimes such as Llama and Llama CPP, developers can run quantized versions of 8 billion to 70 billion parameter models with high throughput and minimal latency. This capability allows developers to perform real-time code completion, security auditing, and document processing without sending sensitive code-based contents over public internet connections. The financial and operational benefits of local execution are substantial for growing engineering teams. Offloading routine development queries from commercial cloud endpoints to local silicon can save organizations thousands of dollars monthly in API leasing fees. Furthermore, local inference guarantees offline availability, removes latency spikes, and protects proprietary source code from third-party data exposure. Our sixth block covers the critical intersection of high-density AI infrastructure and global energy supply. The massive server clusters required to train next-generation models consume unprecedented amounts of electricity, forcing developers to look beyond traditional computing hubs in search of massive, stable, and sustainable power sources. To meet this demand, data center operators are executing major adaptations, co-locating computing clusters directly with clean energy facilities such as nuclear, geothermal, or hydroelectric plants. This direct integration bypasses congested transmission grids, delivering direct, high-capacity electricity to high-density cooling systems and high-performance server blocks. This power co-location strategy is transforming the economics of high-performance hosting. Access to stable, low-carbon energy assets has become a primary bottleneck and a key competitive advantage in the cloud marketplace. In the current compute landscape, securing long-term power purchase agreements is just as critical to technological leadership as procuring state-of-the-art silicon. Turning to cybersecurity and algorithmic governance, The integration of large language models into active business applications has created unique vulnerabilities that traditional firewalls cannot prevent. The most critical among these is prompt injection, where untrusted user input manipulates the model's internal prompt context, causing it to execute malicious instructions. When language models are connected to active tools, such as databases, email systems, or file directories, a successful injection can lead to unauthorized data retrieval, system compromise, or privilege escalation. To counter these threats, developers must implement strict separation between system directives and user inputs, deploy secondary validation models, and run all tools in isolated sandboxes. On the governance front, regulatory compliance is becoming increasingly structured. Organizations must implement auditable logs of model decisions, verify dataset sourcing compliance, and validate alignment guardrails. Building a secure system requires integrating deep learning guardrails with traditional application security standards to create multi-layered defense architectures. To close our analysis, let us outline the actionable technical strategies for the week ahead. First, review your hardware allocation. With compute spot prices stabilizing, analyze if shifting high-volume inference jobs to reserved cloud instances or local developer workstations yields better capital efficiency. Second, design for agency. Start transitioning simple chat assistants into structured multi-agent workflows featuring automated unit testing, reflection checks, and sandbox runtimes. Third, strengthen your system's security. Enforce strict token-level boundaries, implement input and output sanitizers around all model endpoints, and ensure all training and fine-tuning datasets are stored in secure, compliance-aligned environments to safeguard your organization's intellectual property. In summary, navigating the modern artificial intelligence landscape demands rigorous resource management, secure system integration, and advanced algorithmic design rather than simple computational scaling. If you find our daily technical analysis valuable for your system planning and engineering strategy, please remember to click the like button, subscribe to the AI WorkOne channel, and activate the notification bell. Share your thoughts in the comments below. Do you believe inference-time compute will replace the need for massive pre-training runs, or will physical scale remain the dominant factor? I am AI WorkOne. Thank you for joining me for today's deep dive. Keep your systems secure, design clean architectures, and we will return tomorrow with more live updates and compute market analytics. Have a highly productive day and successful engineering.